Hey guys, Mr. Thompson here, and I'm going to get you guys introduced to the Unit 9. Hey guys, this is Mr. Thompson here, and today I'm going to get you guys introduced to the Unit 9 notes over gases. Now, if you didn't pick up the notes in class for one reason or another, just zip on over to my website. You can print them off there under the notes section. Let's get started with something called STP, all right? Now, STP stands for standard temperature and pressure, and you're going to kind of hear this a lot. The standard temperature is 0 degrees Celsius or 273 Kelvin. And we're going to talk about what that means in just a little bit, so don't worry if you've never heard of Kelvin before. Not a problem. The standard pressure is 1 atmosphere. Okay, now there's a lot of different ways to measure pressure, but we're going to focus on atmospheres in here. At standard temperature and pressure, a mole of any gas will occupy 22.4 liters. It doesn't matter what type of gas it is. If you change the temperature, you change the pressure, the volume, or the amount of gas, though, then any of those other variables could change. So, for instance, if I increase the amount of gas, it may take up more volume. Okay, we're gonna kind of talk about. Now we're going to talk about exactly how, because we're not just going to do it as it goes up or it goes down, but we're actually going to be calculating this. And so we're going to go over something called the combined gas law. Now there are 4 variables here. There's going to be pressure, P, volume, V, amount of gas, that's going to be measured in moles, and that is N, and temperature, T. And here's your formula. Okay, now I know that looks a little crazy, but all it is basically a really big ratio. Pressure, volume, number of moles, and temperature, and we're just going to go back and forth with it, okay? It's really simple to use, okay? There are 3 steps that we have to keep in mind, okay? First, you're going to mark out any variables on both sides of the equation that stay the same. So for instance, if it tells you that the temperature doesn't change, then you mark out temperature. We're not going to mess with temperature in that problem because it stays the same. Second, we're going to use some algebra here to get the variable that we want by itself. Before we plug in numbers, we're going to get the variable by itself. It's actually going to save us a little bit of work in the long run, so trust me, you'll want to do that. Now, as you plug in numbers, it's going to be very important. Most of the time, your temperature will be in Celsius, but you must plug it in as Kelvin. So how do we deal with Kelvin? Well, Kelvin is just simply another way to measure temperature. Okay, it's actually better than Celsius and Fahrenheit because you can't have a negative Kelvin temperature. You can have negative Celsius, you can have negative Fahrenheit, but the lowest Kelvin temperature is 0. Okay, so how do you convert it? All you do is you just add 273 to the Celsius. I know that sounds weird, but that's literally all you do. 22 degrees Celsius is 295 Kelvin. Negative 15 degrees Celsius is 258 Kelvin. That's all there is. Now notice I'm not saying degrees Kelvin. I'm just saying Kelvin. It's 258 Kelvin. It's not 258 degrees Kelvin. Okay? Just a little nuance there. So let's take a look at some examples. Okay? Pause the video if you need to read through this example. It's going to be at the top of the next slide, so I'm going to just go ahead and go on forward. We're trying to figure out what is the volume. Now it tells us a sample of gas occupies this volume at this temperature. What if I change the temperature? Now notice it says pressure remains constant. Okay? Pressure remains constant. So when I write my formula, I'm going to mark out pressure. Now the other thing I'm going to mark out, since it didn't tell me I'm adding more gas, then the number of moles are going to actually get marked out as well. The only things I'm dealing with in this problem are volume and temperature. So I can just reduce my equation to look like that. Now, step 2, I want to get what I'm looking for by itself. So I'm going to get the second volume by itself. So I got to get rid of that T on the bottom. Now think back to your algebra. How am I going to do that? I want that T off the bottom. I'm going to multiply. I multiply both sides so I can get that to cancel out, and it's just going to leave me with that V2. And so this is what I get. V2 equals, I don't even have to rewrite anything. It's T2 times that fraction. Step 3, I'm going to plug in numbers. Now notice what I plugged in here. Where did I get that 323? Well, that is 50 plus 273. Remember, you got to convert it to Kelvin. You cannot leave these in Celsius. You will get the wrong answer. So I'm going to plug this into the calculator, and I'm going to get that right there. Notice I left it in milliliters. The original problem had the volume in milliliters, so this is going to be milliliters. Maybe it'll say liters. Who knows? But you don't have to worry too much about that. Let's take a look at another example. All right. This example, I have a sample of oxygen gas, gives me volume, gives me pressure. Says, what will the volume be if the pressure is increased? Notice it tells me temperature remains constant. So again, I'm going to write my formula. I'm going to mark out this time temperature, and again, I'm not adding any new gas, so I'm going to mark out the number of moles. And it's going to leave me with just this. You see, the formula gets a lot simpler once we start crossing stuff out. You don't have to worry too much. All right, it wants to know what the volume will be, so I'm going to get V2, which means I'm going to divide both sides by that pressure, get that to cancel out, and it's going to leave me with V2 equals this. So I just plug in numbers. I don't even have to worry about Kelvin here because there's no temperature. I just plug in the numbers, plug it into the calculator, and get an answer. Now, if we were doing significant figures, I would just write 143 milliliters. But for now, don't worry too much about it. Let's just learn how to use this formula. Take a look at another example. This time it says a rigid container holds 1.5 moles sample of gas at this pressure. I'm adding more gas to the sample, and the temperature is remaining constant. What's the new pressure? All right, get your formula. It says that we are keeping the temperature constant, so I'm going to have to cancel out temperature, but it also gives me another clue. When it tells me it's a rigid container, that means the container shape will stay the same. And if the shape stays the same, then the volume will not change. So we're going to mark out volume, and we're going to mark out temperature. Okay, that's going to leave us with this formula right here. So I'm going to get my pressure by itself. I'm going to get that N off the bottom. So we're just going to multiply, get that to cancel out. This is what I get the pressure to be. Now you really need to pay attention here. Don't fall into the trap. Okay? It says if another 0.25 moles of gas is added, that means my sample got bigger. It will not be 0.25. It will be 1.75 because I added more to it. Don't make that mistake. Plug it in the calculator, and there's your answer. Straightforward, simple. We're going to do a lot of practice with this in class, so make sure you copy down these notes. And if you don't think you got it just yet, don't worry. We're going to practice with this a lot in class. All right. I want to talk about one more thing. We talked about how to do these numerically. I also want to talk about how to do them conceptually. That means we're not going to use numbers. We're going to talk about what will happen without numbers. For instance, if I just tell you that the temperature of a gas is increased, what happens to the volume? Is it going to increase? Is it going to decrease? Or is it going to stay the same? That's the kind of questions I want you to be answering. So there's an easy way to think about this conceptually. Okay? Take your formula. Just take one side of it. You don't even need the numbers. Just PV over NT. Now, if something on the top increases, for instance, if I say pressure increases, okay, then the other variable on top will decrease. So in this case, the volume would go down. Or, if something on the top increases, then something on the bottom will also increase. So maybe the temperature will go up. If pressure goes up, temperature goes up. Okay? It also works the same way if the variables are on the bottom. So let's take a look and see what this is going to be like. Here's an example. Okay, what do you have to do to the volume of a container of a gas in order to increase the pressure if the temperature remains constant? So temperature is not going to be an issue. What do you have to do to the volume to increase the pressure? Well, if we look at our formula, we want to increase the pressure. Volume's on top. We have to decrease the volume. Let's take a look at another. As more gas is added to a rigid, there's that word again, container, what will you have to do to the temperature in order to keep the pressure constant? Okay, well, we write our formula. It says rigid, so volume staying the same. All right, I want to keep the pressure constant. It says as more gas is added, so the amount of gas is going up. Temperature is right next to that, so if gas goes up, temperature has to go down in order to keep the pressure constant. Okay, so the temperature will have to decrease. We take a look at another one. Now, here's something that's interesting. This is a little real-world application here. Why do cars' tires expand in the summer? Okay, well, let's take a look at our formula. Let's think about this for just a minute. Well, let's think about this for just a second. In the summer, it's hotter. That means the temperature is going up. So what's happening? Well, if the tires are getting bigger, we could either look at this from volume or we could look at it from pressure. Either way, though, if the temperature increases, something on the top will say pressure has got to increase also. And that's what's happening. As the temperature gets higher, the gas inside has more pressure. It pushes against the tires more, which expands the tires a little bit. Okay? One last one. Why, if you dip a balloon in liquid nitrogen, does it collapse? Now, I'm going to show you a video of that in just a second. But if we look at it from our formula, okay, I've got a balloon. I'm going to dip it in liquid nitrogen, which is cold, which is going to drop the temperature. And if it drops the temperature, what's it going to do to the pressure of that gas inside the balloon? It's going to drop that pressure. Now, since there's not any pressure in that balloon pushing against it, the balloon, since it's made of latex, will collapse back down to its normal shape, and we get a much smaller balloon.